Hello, 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 hello. Welcome to the 15th stream of Caveman Coding. So, first of all, I just want to apologize for not being there for the past 2 days because I had exams and tests that I should take, which are not related to programming. I mean, at least in the sense of programming on the computer. So I was not able to stream, but yeah, we're back again. We're back again with intent right now. So we're back again with intent, and um, let's program for some time. Some programming every day doesn't make you sad, right? Okay. So today is Jan 21st. So I created the Vim. So and today we will be doing Vim uh, because uh, because um, because I just want to optimize my workflow using Vim. Not optimization, but I was just on Primogen's the Prime Times stream, and he was talking about um, the optimization in your early days or the early hours basically. So he was of the he was like, um, don't try to optimize too early. That's what it was. So if you're trying to optimize your 12 hours a day, that's good. But if you are trying to optimize 3 hours a day, 3 hours of work a day, and 3 hours of work a day is not much, and you are trying to optimize it, I don't think it's beneficial. So once you hit that hours uh, target per day, um, you will you will get benefit from it, and you will try to um, you will maximize your output, and your optimization will give you success. So today, yeah, okay, that is yeah, that's what I was seeing on the Paramagen's stream. So yeah, so once we start programming at least 4 hours a day, that's the goal. But I don't think that's I mean, it is possible, but to stream 4 hours a day, it's kind of hard. But we need to do it because I need to manage my college also by streaming. So but I will try to do. I'm sorry. Sorry for that. So yeah, my point is, I will um, try to stream every day. So I'll try not to miss too many days, and I'll try to be disciplined by now. From now, not missing too many days on a streak. So yeah. Okay, enough of talking. So today we will do. So I'll show you what we're doing today. So this is what we're doing today. This is the project I want to take upon. So it's very exciting that we're doing the project. So yeah. So did I not copy correctly? Damn. Alright. Alright. So this is the project that we're doing. Light mode is good. I know I may be a psycho from by using light mode, but I don't know. I just try to it just looks better. I think so. I'm kind of get I kind of got tired of the dark mode, so this is it for now. So yeah, so this so we will be doing this, and there are table of contents. There's intro, getting started, IRS, ICV. Oh, I'm sorry. for those who are, um, unfamiliar with this project, I think it's best to read this and explain it to you. So I'll try to explain it to you once I read this, because I'm also, even for me, this is the first time I'm on this website. So yeah, we will explore this website together, and we will try to build an OS in 1,000 lines, as this website says. All right. So yeah, let's start. Hey there. In this book, we're going to build a small operating system from scratch, step by step. You might get intimidated by when you hear OS or kernel development. That is right. That is very true. The basic functions of an OS, especially the kernel, is surprisingly simple. Interesting. Even Linux, which is often cited as a huge open source software, was only 8,413 lines in version 0.01. Today's Linux kernel is overwhelmingly large, but it started with a tiny code base, just like your hobby project. Nice. So this will be our hobby project, I guess. So let's see. So we'll implement basic context switching, paging, user mode, a command line shell, a disk device driver, and a file read write operation in C. Sounds like a lot, however, it's only 1,000 lines of code. So let's try it again. Read this sentence carefully. It's just what it is. So I just want to read this sentence again. So this is context switching, paging, user mode, and a command line shell, and a disk device driver, and file read write operations in C. Okay, so the context switching, paging, user mode, a command line shell, a disk device driver, and file read write operations in C. You'll have to do it. C programming. Let's go. One thing you should remember is it's not as easy as it sounds. The tricky part of creating your own OS is debugging. You can't do enough debugging until you implement it. Crazy. You'll need to learn different debugging techniques and skills you have never needed in application development, especially when starting from scratch. You'll encounter and challenging parts like boot process and paging, but don't worry, we'll also learn how to debug in OS too. All right. That's crazy. So the tougher the debugging, the more satisfying it is when it works. Wow, that's a statement. Let's dive into exciting world of OS development. You can download the implementation examples from GitHub. This book is available under this, and the implemented examples and source code and then text are under the MIT license. Okay, prerequisites are the prerequisites are familiarity with C language and with the Unix environment. If you have GCC hello.c and dot slash a dot out, you're good to go. The book was originally written as the appendix of my book. This thing written in Japanese, happy OS hacking, brilliant. Alright, so I think it's pretty simple, and I think we'll learn a lot by this project. So yeah, that's the reason I chose this project, because I think it's very important to do it. So to understand the OS and thereby increase our programming skills, and also um, the knowledge of the computer and and the operating system itself. So let's get started. So getting started. So install Homebrew and run this command to get all tools you need. So alright, so we'll install this. So let's go. Yeah, as I told you, I'm using Vim, not VS Code. Um, yeah, because Vim is better, as they say. So I'm trying out Vim, if it is actually better than VS Code, and you know, even if it's not better, I'm just trying to learn Vim and make Vim as my primary editor and get used to Vim. So the command is this: brew install llvm lldqemu. Alright. Motto updating homebrew. Oh, we did not do homebrew updates. I think for a long time we did not do homebrew updates. So okay, it's taking time. Oh my god. Oh my god. Oh shit. Oh shit. The thing is, I just touched my collarbone without realizing that I am touching my collarbone. If you do not know, I just well, I 2 weeks back, I exactly 2 weeks back, I fell off my bike and fractured my collarbone, and ever since that, I've been wearing a sling to my hand and a belt to my chest, so that my collarbone is healing, and I mean gets healed, and hopefully, you know, I resume operations like a normal human being. Um, so yeah, that's that. So I just touched my collarbone without even realizing, because I was feeling itchy there. So what is it doing now? So fetching CA certifications, fetching SQLite, fetching Python at 3.13, fetching Z3, fetching LLVM. What is LLVM though? LLVM, which is blobs. Okay. So LLVM. Well, it's taking a lot of time. I did not expect it to take this much amount of time for just updating. Alright, let's just wait. Capstone, get text, LLD. Okay, DTC. DTC. Python packaging. Snappy and VDE. All these random names that I've never heard of, but okay. glib. What is glib? Libtasnal. Okay, keeps updating, but yeah. Let's go to the website and see. Alright. Setting up a Git repository. So, see, I know how to use a Git repository, but I'm not very confident in it, and I think this will be a good, you know, I think this will be a good exercise to do it, but I have to set up Git repository now. Oh my god. Set up a Git repository. Let's do it. Let's try to do it. So initializing a new repository jet in it. Okay, let's do that. Oh, it's still running. It's still updating. Is my mic on though? It is on, okay. Alright, that's on. The screen has freezed there. Why is it freezed here? I'm just gonna. 1 second. I'm just gonna set it back uh, to to how it should be. Just give me a second. Just give me a second. I'll fix it. Alright, that's good. Cool. Alright. So already downloaded. So why are you downloading it again? Dude, come on now. Come on now, like why is it taking so much time? Okay, let's just open a new terminal. Let's just open a new terminal, right? I just want to open a new terminal shell. New window with convert new window. Let's do a new window. Um, just copy this path. Sorry. Or just wait till till this till this finishes. Fetching curl. I did not expect this to run this long though. Let me just fix this screen. I did not. Okay, so this is not finishing anytime soon, but let's just create a JIT in it. Create a JIT repository here. Initialize the empty repository. That's cool. Now what do you do? Versioning an existing repository needs your repository. Okay, that's cool. JIT init pointing is in an action project directory will execute the same instance step as mentioned above. Scope to the project directory. Okay. Cloning an existing repository. JIT clone. No. Saving changes to repository. JIT add and JIT commit. Okay. Report remote collaboration jet push. Configure setup jet config jet remote add. Once you have a remote repo setup, you need to add a remote repo URL to your local jet config. That's just okay. That's cool, man. Okay, it's okay. That's cool. Setting my jet repository optional. No. So if you wanna do this, then what are the do we have a jet ignore file? So we are in .jet, alright. Ignoring, so this thing head config description. So you want a jet ignore file? I don't know what it is. I actually don't know what jet ignore is. What a jet ignore file is. Jet ignore. Okay, that's cool. Alright, so that is cool. It has updated everything, so that's cool now. Let's go back this in the future. Now let's see that later. But okay, so let's. So we have JIT here. So not too sure setting up a repository. Well, we have set up a repository right here. Cloning an existing repository. Cloning project is already set up in a central repository. The clone command is the most common way for use to train local development clone. Like jet cloning is generally a one-time operation. Jet tag, jet commit, inspecting a jet tag, jet blame, undoing changes, rewriting history. So saving changes, jet commit, inspecting jet add basically. Jet commit, jet diff, dot jet ignore. This is what we need. So change every file in your working copy as one of these three things. Track the file which has already been staged or committed. Untrack the file which has not been staged or committed. Okay. So now in stage is committed a file which Jet has been explicitly told to ignore. Ignore files usually build artifacts and machine generated files that can be derived from your repository source or should otherwise not be committed. Okay. Some common examples are dependency cache, such as the contents of node models or packages, and compile code such as this. Build output directories such as this. Files generated at runtime .log at temp. Hidden system files .dstore thumps .dap. How do you open a jet ignore file? How to open a jet ignore file? Okay, let's do that. You can just do vim, I think. Vim.jetignore. Alright. We are in jetignore. Let's copy this. Insert. Do that. and then escape, save this. Cool. After saving it, now we are done. And then let's go this to this RASCV 101. Just like web browser hide the difference between Windows, Mac OS, and Linux, operating systems hide the difference between CPUs. In other words, um, operating system is a program which controls the CPU to provide an abstraction layer for applications. Okay, so the operating system hides the difference between CPUs. In this book, I chose RASCV as the target CPU because specification is simple and suitable for beginners. It's a trending ISA instruction set architecture in recent years, along with x86 and ARM. The design decisions are well documented throughout the spec and they are fun to read. We will write an OS for 32-bit RASCV, of course. RASC5 is it called? Okay, RASC5. Of course, you can write for 64-bit RASCV 5 with only a few changes. However, the wider bit width makes it slightly more complex, and the longer address can be tedious to read. QEMU word machine. Computers are composed of various devices: CPU, memory, network cards, hard disk, and so on. For example, although iPhone and Raspberry Pi use ARM CPUs, it's natural to consider them as different computers. Okay. In this book, it's about QEMU word machine because even though it does not exist in the real world, it's simple and very similar to real devices. Okay, you can emulate it on QEMU for free. You don't need to buy a physical hardware. Okay. Okay, when you encounter you can emulate it on QEMU for free. You don't need to buy physical hardware. Okay, when you encounter debugging issues, you can read QEMU source codes or attach the debugger to the QEMU process to investigate what's wrong. So RASCV assembly 101. So we're trying to learn the architecture assembly code basically. So IIC5 or IC5 ICA instruction set architecture defines the instructions that the CPU can execute. Okay, it's similar to ABIS, a programming language specifications for programmers. So it defines the instructions that the CPU can execute. It's similar to APIs or programming language specifications for programmers. Okay, so it is the programming language specifications. Okay, when you write a C program, the compiler translates it to RSC file assembly. Unfortunately, you need to write some assembly code to write an OS, but don't worry, assembly is not as difficult as you might think. Okay, fun tip: try Compile Explorer. A useful tool for learning assembly is Compile Explorer and only Compile. As you type C code, it shows the corresponding assembly code. Okay, that's cool. That's actually very cool though. As you type C code, it gives you assembly code. Alright. Okay, so int square. So this is the function and this is the assembly code. So push RBB and then return, which is move EX. For the x86 architecture, this is the assembly code. Interesting. dword ptr. I don't understand a single thing here, but I guess that's cool. So there's a lot of architectures. Let's just try to search for RAC5. Okay, it is there. Oh, nice. Okay, RAC5 is what we understand, what I understand. Okay, this is what I have learned in school, not school. And I SPSP minus 32, 28 of SP, 24 of SP, and then that I store value. Is it store value? I'm sorry. Is it this move value, multiplication, addition, SW store vector or something? I don't know. Store weight? I'm not sure. So by default, specify RSCV RV G32 clang trunk. Okay, we need to do that. Okay, is it RASCV? Yeah, it is this. Okay, I'm sorry. It is this RASCV RV32 GC clang of trunk. Alright. So also it will be interesting to specify options like -00, -00, optimization off, or 0 to optimization combine options and see how the assembly changes. Okay. The options, where are the options? No. Change it to C. Where are the options? Optimization options. Okay, that's cool. Um, Still okay. This will be RASCV. Um, Clang of trunk. Alright, that's what we need. Assembly language basics. So it's a mostly direct representation machine code. Let's take a look at the simple example. Add I A0 A1 123. Typically, each line of assembly code corresponds to a single instruction. Okay. The first column add I is the instruction name, also known as the opcode. The following columns A0, A1, A23 are the operands, the arguments for the instruction. In this case, add I instruction adds the value 123 to the value in register A1 and stores the result in register A0. Cool. Registers are like temporary variables in the CPU and they're way faster than memory. CPU reads data from memory to registers, does automatic operations on registers, and drives the results back to memory or registers. Here are some common registers are SCV. So they are like temporary variables in the CPU and they're way faster in memory. CPU reads data from memory to registers, does automatic operations on registers, and drives back the results back to the memory registers. Here are some common registers in RSCV. Register PC, ABI name is the alias. PC description program counter where the next instruction is. Okay, these are the where registers basically. X0 is 0, hardwired 0, always reads as 0. X1 RA return address. X2 SP stack pointer. X5 and X7 T0 minus T2, which is temporary registers. Okay. X8 is FP stack frame pointer. X7 minus X11 A0 minus A1 function arguments return values. X12 minus X17 A2 minus A7 function arguments. X18, oh, not minus, it is 2 basically. So X18 to X27 is ABI name is alias. S0 to S11 temporary registers saved across calls. 28 to 31 as temporary registers. Okay, there's a lot of theory here. So generally we may use CPU registers select, but if they could interoperate with other software or registers are used as well defined, it's called the calling convention. Okay. For example, registers are used for function arguments return values. Okay. For human readable, they are given addresses like A0 to A1. In the ABI, check the spec for more details. Calling convention. Memory accesses their limited number. Most of the data are stored in memory. Programs reach areas from or to memory using the LW load word, yeah. SW store word instructions. Load word A0, A1. Read word 32 bits from address in A1 and store in A0. And see, this would be A0 equal to pointed to A1. So read a word from address in A1. Okay. Alright. I store in A0. That's cool. Store word A0, A1. Store word in A0 to the address in A1. And C, this would be pointed to A1 is equal to A0. Okay. Okay. Cool. Nice. You can consider dot 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 as a pointer dereference in C language. In this case, A1 is a pointer to 32 bits wide value. Hmm. It's a pointer dereference, okay. Branch instructions change the control for the program. They are used to implement if, for, while, and loop. Bean as A0 label. Go to label if A0 is not 0. Continue here, label. If A0 is not 0, continue here. Bean as stands for branch if not equal to 0. Other common branch instructions include BEQ branch if equal and BLT branch if less than. They're similar to go to in C but with conditions. They're similar to go to in C but with conditions. Alright. Branch if equal and branch if less than. Okay. So branch Bness is basically branch if not equal to 0. Go to label if A0 is not 0. Okay. Nice. Nice. Function call. JAL, jump and link, and ret. Instruction used for calling functions and returning from them. Oh, nice. JAL is jump and link. Load 1232 A0 register function argument. Load 123 to A0 register function argument. Okay. So A0 is function argument because A0 function arguments and return values. A0 is a function argument, A1 is a return value. That's cool. Nice. JAL array label, jump to label and store the return address in the array register. After the function will continue here. Int function interface. A is equal to plus or is equal to 1, return a. Label is equal to add I A0 A01 increment to A0. So this is a label, basically jump to label. This is the function. Increment A0 for argument number 1. Okay, return to the address stored in array. Yeah. Okay. Return to the address stored in array. That's cool. A0 register has the return value. Nice. A0 register has the return value. Well, nice. 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 Very cool. Nice. Very cool. Function argument is passed in A to A7 and the return value is stored in A0 as per the calling convention. Nice. 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 Stack. Stack is the last in first out memory. Yes, stack is the last in first out memory space used for function calls. So stack is used for function calls and local variables. It grows numbers, and the stack pointer sp points to the top of the stack. um, okay. Nice. To save a value into the stack, decrement the stack pointer and store the value, aka push operation. Nice. Move the stack pointer down by 4 bytes, that is stack allocation. So add I is basically sp minus 4, okay. Sp is equal to sp minus 4, okay. And then store w, store where the store a0 to stack, okay. And then load a0 from the stack. To load the value and increment the store stack pointer. So load a0 from the stack, okay. One second. LW is, yeah, from address in a1 stored in a0. Okay, yeah, that's what happens. Okay, load a0 from the stack, okay. Add I is sp4, move the stack pointer by 4 bytes. Generable comparison, so we don't have to write them manually. CPU modes has multiple modes, each with different privileges. In RASC5 there are 3 modes: M mode, S mode, U mode in OpenSBI. Okay. Mode in with kernel operates kernel mode. S mode is the kernel mode. Okay. U mode is the user mode. Oh damn, that's nice. Privileged instructions. Among CPU instructions, there are types called privileged instructions that applications user mode cannot execute. Okay. Opcode and operand CSSR, RD, CSR. Read from CSR. Pseudocode is RD is equal to CSR. Okay. Write to CSR. Okay. Read from it and write to CSR at once. SRET return from top trap handler and all this inside inline assembly and all this stuff. Okay, I will do this tomorrow. This is a short stream for today, but yeah, I'm a little tired for today, so